So as we talked about in class today, we're moving on from salts into the area of buffers. And buffers, of course, are very important in the human body, in industry, etc. And so it's important to understand how they work. An example of a buffer that was given in class is the combination of acetic acid and sodium acetate. And this combination of a weak acid and its conjugate base is able to resist changes in solution pH when a small amount of strong acid or base are added. And notice that we say that it has the ability to resist changes in pH. In other words, the pH, rather than not changing at all, changes a small amount. So we looked at the reaction of a strong base, which reacts with the acidic part of the buffer, the one with the extra H. And then in this case, we noted that it made water and acetate. And of course, because in the reaction, we're using up all of our hydroxide and producing a weak base, it's in a sense, we're exchanging a strong base for a weak base, which is why the pH doesn't change as much as it normally would. So we're getting the buffers kind of soaking up the hydroxide and producing acetate. And as we know from our study of salts, that's a weakly basic ion. The opposite effect happens when you add a strong acid. It reacts with the basic part of the buffer, which is also presumably in excess. And in this case, we produce chloride ion has a pH of 7, although it has a negative charge. Remember that it does not do a good job of acting as a base because its conjugate acid is a strong acid. Okay? So we produce something neutral and something weakly acidic, and in essence, we're exchanging the strong acid HCl for the weak acid. So the pH goes down, but just a tiny bit. So in both cases, what happens to the pH? It changes, but slightly. So some examples of buffers, we might, for example, have H2CO3. And remember that that would be a weak acid. So we would want to have that in combination with its conjugate base. Remember that would be HCO3 minus, okay, because it's lost a proton, and because you can't just have HCl3 minus, you would often see this as written as a salt. We do not normally write the ionic compound with these positive and negative charges, so get rid of those. So the sodium hydrogen carbonate would be the weak base. Okay, so this would be an example of an effective buffer. It has to be a weak acid with the conjugate base. Okay, so another example might be, well, how about a weak base? Let's use ammonia. And that could be in solution with its conjugate acid. Okay, well, the conjugate acid of NH3 is NH4+, but you can't buy a bottle of just NH4+, so this would have to come as a salt. So once again, you'd have something like NH4Cl, perhaps, or NH4Br, and once again, that salt would be written as the neutral compound, NH4Cl. Okay, so these are two examples of what a buffer might look like. Notice that they're both weak, and they both have conjugates that are weak. Some combinations that would not be examples of buffer, well, maybe something like HCl and NaCl. Okay, and the reason that this is not a buffer is because although we have an acid, HCl, in combination with its conjugate base, Cl-, HCl and Cl- cannot coexist in solution. As soon as we put HCl into water, it's going to give away its protons and make Cl-. So there won't be any HCl sitting around waiting to soak up any excess acid that's added. Okay, so this does not work as a buffer because it's a strong acid with its conjugate base. Okay, another thing that sometimes people will think is a buffer is if they take a weak base and put it in solution with a weak acid, say acetic acid. Okay, notice that these are both weak, but they are not conjugates of each other. In other words, if we put these guys together with each other, they would actually react with each other and make new substances. So that doesn't work. Okay, one other non-example that you should be aware of is something like H2CO3. Okay, so once again, we're using that same weak acid as we used before over here, but let's put that in combination with Na2CO3. Okay, that almost looks like a buffer. CO3 2-, which is what that would be when the sodium carbonate dissolves in water, is a weak base. But notice they are not conjugates of each other. So this weak acid has 2 protons, while this CO3 2- has no protons. And in order to be conjugates, they need to differ by only 1 proton. Right? So those are all non-examples. So watch out for examples that show you a strong acid with its conjugate base or a strong base with its conjugate acid. Okay? Those are not examples of buffers. Watch out for examples where they're not conjugates of each other, either because they're completely different, like these two, or where they're different by more than 1 proton, so they're not conjugate, like in this example here. All right, so let's move along a little bit and let's look at how we would actually calculate the pH of a buffer solution. Now you might think, oh dear, another type of calculation that I have to learn. But the cool thing about these is that you've done this calculation before. There's just a little twist that you need to be aware of, a couple little twists. Okay, so the first thing is it says calculate the pH of this solution, and you're given 0.040 molar sodium acetate and 0.08 molar acetic acid at 25 degrees. And you're given a Ka. Okay, so that's very familiar. So in this particular problem, just like above, either one of these substances can be our reactant. Okay, so remember up here, if we were adding hydroxide, we reacted the hydroxide with the acetic acid, the acidic part of the buffer. And if we were adding the strong acid, we reacted it with the basic part. So depending on what was added to the buffer, we chose a different component of the buffer to react. All right, so we can do the same thing with this type of problem. We're trying to figure out the pH. So what we're going to do is we're actually going to pick one of the 2 components of the buffer to react. All right, and I'm going to go ahead and I'm going to pick the acetic acid. Now notice we don't have anything else. In this problem, there's nothing else in the solution. We're not adding a strong acid. We're not adding a strong base. All we have are the 2 components of the buffer solution. So therefore, we're not going to be adding HCl or NaOH or anything. Okay, instead, we're going to react one part of the buffer, once again, with water. Okay, because now in this problem, there's no additional strong acid or strong base. And again, we're down to having a weak acid. Okay, and water's a weak base, so we're going to have an equilibrium. And just as we've seen before, the acetic acid donates its proton to water and makes H3O+. So notice what happens. One component of the buffer is generating the other component. So sometimes people will wonder, well, why do I have to react the acetic acid with water? Why don't I react the acetic acid with the other part of the buffer? Well, what happens in that case is if I transfer this proton over to the acetate, I end up making acetate again, because this is losing its proton, and I generate acetic acid as well. So notice what happened. This and this are the same, and the acetic acid's the same on both sides. Okay, and so this is not a chemical reaction that produces new products. It's if you were going to write this out and look at it, you would say no reaction, because overall nothing really has changed. Okay, so you can't just react the 2 components of the buffer with each other. They probably do react with each other, but if you do that, it's no overall, you don't get an overall change. So we call that no reaction. So don't do that. Pick one component of the buffer, react it with water, and then it'll generate the other part. Okay, the other thing that people will wonder about is, well, how do I pick? Okay, why did I start with the acetic acid rather than with the sodium acetate? Okay, and it doesn't really matter. You can actually use either one in your problem and react it with water. However, it's convenient in this problem to pick the acid because I'm given the Ka. So remember, the Ka describes the reaction of the acid with water. So it's easier just to go ahead and use the acid. All right, so now we're trying to figure out the pH. We have something that is an equilibrium, right? And so at this point, remember that you just are going to use an ice table. We're going to calculate the H3O plus at equilibrium. We're going to get this value. Once we know that, then we can get the pH. Okay, so it should be very familiar to you. All right, so initial concentration of acetic acid is 0.080 molar. And water we can just ignore. Okay, so think about what you would normally do now if you were setting up your ice table. This value would normally, this value here, your acetate initial concentration would normally be what? 0. But in this case, we have a buffer. So we have substantial amounts of both components. And so 0.08 molar for the acetic acid, the initial concentration of the acetate, or the CH3COO minus, is 0.04. So in this case we have two that have an initial concentration. And our hydronium will still say is approximately 0. Okay, so now we're going to do an ice table problem, but it's just a little different because we have initial amounts for two of them. Okay, in this case, since we have a low amount of hydronium over here, the equilibrium is probably going to shift to that side, going to the right. So let's go ahead and make this minus X. And this plus X. And this plus X. Okay, and so now we have our equilibrium amounts. We have our K value. So we would say Ka, and that's, of course, equal to H3O plus, which is X, times the acetate, which is 0.040 plus X. So we have our two products, product times product, and we're going to divide that by the concentration of the reactant. Except notice that since our Ka is fairly small, since it's 10 to the minus fourth or lower, we can usually do what? That's right, neglect X. So I can get rid of this X because we're saying this is such a small change that it's not going to make that much difference in the 0.08. And hey, 0.04, that's a pretty big number. So this small little change of X is probably not going to matter. So we can get rid of that one. Okay, so notice these are both non-zero numbers. And so X compared to them is going to be pretty small. Now this X over here, we have to keep because it's basically compared to 0. All right, so we're going to get rid of this, get rid of this. So our problem ends up being 1.8 times 10 to the minus fifth equals X times 0.04 divided by 0.080. We solve for X, we multiply both sides times 0.08. We divide both sides by 0.04. We get X equals 3.6 times 10 to the minus fifth molar. That is our hydronium ion concentration. So we just take the minus log of that X, and that will give us our pH, which is 4.44. Okay, so notice what's happening here. We're essentially just setting up an ice table, just like we've been doing for many weeks now. in at least a couple weeks with acids. And the only thing we have to pay attention to that's a little different is we have to remember that the initial amount of two things is given in the problem. So we have both the acetate here and the acetic acid. The change can be neglected in two places, okay, which actually just makes our life easier. And when we solve and get our pH, we can find out that this, even though this buffer has both acetate and acetic acid in it, the pH of it is overall acidic. Okay, so all buffers will have a pH that typically is either acidic or basic, depending on the Ka and Kb of the acid and base, and also depending on their starting concentrations.